Phase shift is the measure of the time difference between the peaks or any other corresponding point of an input signal and its filtered output. In first order filters such as RC or RL circuits, the output is not only attenuated in amplitude but also shifted in time relative to the input. This shift is expressed as an angle in degrees or radians and reflects how the reactive component, which is the capacitor or the inductor, delays the signal. For beginners, think of phase shift as the lag or lead introduced by the filter, which is crucial when signals must be synchronized. Well, let's have a look at some of the mathematics that define phase. For a basic RC low-pass filter, here's a transfer function that you've seen also before. Now, the phase shift, which is denoted by the Greek lowercase letter phi, is the angle of this complex function and is defined as the negative arctan of omega RC. And this means that at low frequencies, when omega RC is a small number, phi is approximately 0, so the output is nearly in phase with the input. But at high frequencies, when the omega times R times C is a large number, phi approaches minus 90 degrees, indicating that the output lags the input by a quarter cycle. A similar analysis applies to other first-order filters, though the specific phase shift formula may vary depending on the circuit configuration. Here's a Python script that calculates and plots the phase shift for an RC low-pass filter over a range of frequencies. This visualization can help you see how the phase shift changes from 0 to minus 90 degrees as frequency increases. In this example, we keep the component values for the resistor and the capacitor the same, and the only thing that would change is the input frequency. When you run this script, the plot will show the phase shift in degrees as a function of frequency. Notice that at lower frequencies, the phase shift is close to 0 and gradually approaches minus 90 degrees as the frequency increases. When I first came across the phase shift concept, I did struggle to understand it. When I first encountered the concept of phase shift, I found it quite challenging to grasp. However, I discovered that visualizing phase shift in the time domain instead of the frequency domain was beneficial. For many people new to intermediate electronics, thinking in the time domain is more intuitive than considering the phase or thinking in the frequency domain. So I hope that this explanation that follows aids you in understanding phase shift as well. So phase shift can be understood in terms of time delay, just like in lag of phase shift in terms of degrees. For a sinusoidal signal with frequency f, a phase shift of phi degrees translates into a time delay that is given by this formula. So delta t, the time delay, is equal to phi, the phase shift, divided by 360 times f, where f is the frequency. And this works because a full cycle of 360 degrees corresponds to one full period, where period, denoted by the uppercase letter t, is equal to 1 divided by f, and that's in seconds. In other words, if one waveform is shifted by a certain phase angle relative to another, this phase difference means that one waveform is delayed or advanced in times by delta t. And again, to demonstrate this in a programmatic way, I've put together this simple Python script. It generates two sine waves at a frequency of 10 Hz. One sine wave has no phase shift and the other is shifted by minus 45 degrees, illustrating the corresponding time delay in the time domain. When you run the script, you'll see two sine waves, one without any shift and one delayed by the computed time interval. The visualization here demonstrates how a phase shift expressed in degrees directly relates to a time delay in the signal. And of course, you can play around with the script to see what the time delay is like for other frequencies and other phase delays. So same frequency, different phase shift. Even though both signals share the same frequency, the phase shift arises from the reactive component in the circuit. These components introduce the time delay, as you learned already, due to the frequency-dependent impedance, which has an inherent phase angle. I want to have another look here at the phase shift that is caused by different capacitor values. So in previous examples, we varied the frequency. Now I'm going to also vary the capacitor and see what the effect of this change is. So we're going to change both capacitor values and have a look at a different range of frequencies. So in a RC low pass filter, the phase shift is given, as you know, by this formula, where R is the resistance and C is the capacitance. And omega here, lowercase omega, is the angular frequency. The product RC is the time constant of the circuit. When you change the value of the capacitor, it directly alters this time constant, which in turn shifts the phase response. For a fixed resistor, increasing the capacitor value increases the RC value, and that causes the phase shift to occur at lower frequencies, whereas decreasing the capacitor value shifts the phase response to higher frequencies. And here's yet one more Python script. This script plots the phase shift for several capacitor values while keeping the resistor value constant. This visualization demonstrates how varying the capacitor value changes the phase shift behavior across the frequency spectrum. And as you can see in this plot, I've calculated the phase shift for an RC circuit for 3 different capacitor values. So the plot generated by this script illustrates that for fixed resistor values, when we have a larger capacitor, the phase shift transitions more quickly. And as a result, the phase shift approaches minus 90 degrees at lower frequencies. And when you have a smaller capacitor, the phase shift remains closer to 0 degrees until much higher frequencies are reached, and the transition to minus 90 degrees is delayed. So I hope that this demonstration explains and demonstrates the importance of the capacitor value in tuning the phase response of an RC filter. So by selecting an appropriate capacitor, you can design filters with desired timing and phase characteristics to suit your specific application. Let's have a look at the key takeaways from this lecture now. First, the definition of the phase shift. So phase shift quantifies the time delay between an input and its corresponding output signal in a filter, and that's expressed as an angle in degrees or radians. In an RC low-pass filter, the phase shift is given by this formula, which shows that as frequency increases, the phase shift transitions from approximately 0 degrees to minus 90 degrees. A phase shift of phi degrees corresponds to a time delay of delta t, and that links the angular phase differences to actual time delays. So this formula is important if you want to translate phase into time. The values of reactive components, such as capacitors and inductors, directly affect the phase shift. In an RC filter, increasing the capacitor value increases the time constant RC, and that results in an earlier, low frequency onset of significant phase shift.